Hey everyone, today let's look at the application layer of system design. So we shall look into the following topics today. First we'll look at resource sharing, then load balancing, followed by client-side storage and edge computing. To scale up your application, you can either scale your resource horizontally or vertically. So, vertical scaling refers to adding more power, that is, in terms of CPU and RAM, to an existing machine. So, if your machine initially had, let's say, 32 GB of storage, you can 32 GB of RAM, then you can scale it up to 64 and to even 128 or 256 GB of RAM. So that's vertical scaling. And horizontal scaling refers to adding more servers to your resource pool, so that more shared computation could be done. So, in reality, horizontal scaling is almost always more desirable than vertical scaling. This is because you don't get caught in a resource deficit. That by that what I mean is, when you are actually scaling up using vertical scaling, there will be some downtime to your resources because you are changing the hardware configuration of something that was already serving some requests. So but in case of horizontal scaling, those servers which were initially there, when a new server comes up, these server can actually, there won't be any downtime. The additional resources can be integrated seamlessly. On top of that, vertical scaling is not feasible at times because, let's say, you already have a 128 GB RAM and a good enough CPU in your server. It's very hard to upgrade from that because it is very expensive. Also, it's not available well, because the most of the industry servers that currently exist use 128 GB of RAM. So it is not feasible most of the times to go for vertical scaling. So let's now talk about load balancers. So instead of client application directly interacting with the application servers, in most cases, what they do is they interact with load balancers. So what load balancers are they are a set of machines. They're same as servers, which is an order of magnitude lesser than the number of application servers you have. So let's say you have 100 of application servers, then you would have almost like 10 load balancers which the client would be interacting with. So the client can send a request to any of the load balancer, who then forwards this request to a working application server. So why do we need this load balancer? So the answer was already in my previous statement. It sends the request to working load balancers. So in case of a dying servers, the load balancer know which of them is alive, so that can serve the request to your client. On top of that, there is a concept of load balancing in system design. So since you have so many application servers, you want your requests from the clients to be almost evenly distributed between these servers. So that's called load balancing. So the load balancers actually does this in the sense that it actually distributes the load between the servers to maintain the balance. So usually in case of simple load balancers, round robin algorithm is used. That's a simple, let's say, if you have this one load balancer would first reroute this to, let's say, this pool number one, and then two, and then three, and then it would go back to one. So it's like a modular operation. But this is very naive way to do it, because there can be load imbalance here, and in more complex system, the load balancers actually communicate with the application servers and know how many requests they currently have, and then try to have a policy such that they get distributed evenly. So, uh, taking a step further, in some cloud providers such as Amazon, they do have elastic load balancer. So, what that means is elastic load balancers have two tiers of load balancing. The first is across physical geographical areas, or also known as domains. So, and there one load balancing happen, after which there is a load balancing happening in the actual physical servers within that domain. So for an example, you're streaming some video from, let's say, Amazon Prime. Then first the load balancer will check whether any server is available close by. So I'm in India, so it will first check if any servers are available in India. That's our first layer of load balancing. After which, if it's available, then within India, which server should the video be served from. So that's elastic load balancing. So let's now talk about the client side storage. So storing data in client side is one of the most effective way to improve the latency and to provide a good user experience. And yeah, so for desktop and mobile applications, it has great flexibility in terms of client side storage, uh, because readily you can store whatever you need in the OS. And so let's discuss various client side storage in web, which is not that trivial. So first we have cookies. So cookies are bit of information either sent by the server or set on the client that are saved use locally on the user's browser. So for each website, some kind of a cookie would be stored by the browser you are using. So they are automatically attached to every request from that website. So since so one of the most common scenarios where these cookies are used is for authorization tokens. So once you actually logged into some website, then you don't actually have to log in again, because some kind of cookie data would be stored for that website, so that you don't have to log in again and again. So coming next, we have this web storage API that is there in most modern browsers now. So these APIs provide you the simple persistent storage. You can store simple name value pairs of data, and this can be stored either for just one of the users session. So in when a user is visiting your website and the tab is still open, then that storage would be there. Once it's closed, it's going to be flushed. Or you can even have local storage, where in this case, where even when the user is visiting your site for a second time, the data that he had before would still be there. So I think one of the good examples here is in some of the e-commerce websites you have this cart. So likely this is going to be stored using this web storage API. Okay, so next we have indexed database. So indexed database is an API for storing and retrieving data using an indexed transactional database of key value pairs on user's computer. So previously we had this web SQL databases commonly available in all the browsers. It was a familiar to use. It was easy in terms of familiarity because SQL is known to many, and coming to the rise of IndexedDB, which provides much more advantages over web SQL, which I'm not going into detail in this video. The web SQL database got obsoleted. So compared to web storage APIs, IndexedDB can also store more complex stuff and persist them locally. Okay. Now another important storage that's done in the client side is most modern browsers support HTTP caching. So caching HTTP responses to specific requests. So that is very useful for doing things like storing website assets offline, so that when the site, if say you have lost your internet connection, then also the website, everything would be rendered properly. Also, some functionality would be available since you have cached most common HTTP responses that you're going to get. Yeah. So let's now talk about edge computing. Edge computing refers to computations that takes place outside the edge of internet. So as opposed to cloud computing, where computation happens in the centralized location in some servers, edge computing typically execute close to your application itself, that's close to your data source. So what are the advantages of using it? One obvious advantage is the latency. The time in case of cloud computing, your request from the applications has to go to the cloud, so there is a network latency there, and then the processed data should come back to you. But in case of edge computing, most of the computation happens within the applications itself, so they are not that much limited by factors like bandwidth, network speed, and even the distance of server or database. Okay. So, one scenario where this most prevalent that I can think of is in case of smart vehicles. So, let's say there is some image processing happening for detecting a pedestrian in a smart car. If you were to do a cloud computing there, unfortunately, if your network, there is a disruption of your network midway and the pedestrian crosses the road, you are going to hit that pedestrian if you were to do cloud computing, because you don't have the compute capability which you are in from the cloud. But if you were to do edge computing, if you were to do the computation within the car itself, then you could still do this because you are not limited by the cloud. So the next obvious advantage is enhanced security. So nowadays there are a lot of data that's getting leaked from the cloud because of less stringent security measures. So if you were to store things locally using the client storage mechanisms I told before, it would give, and using edge computing to do most of the tasks, that would give you enhanced security for your data. Also, if you process your data by means of edge computing and then save it to the cloud, it would be less susceptible to attacks also. Okay. The next obvious advantage is that you can reduce the infrastructure, because most of the computation will be done by the applications themselves, so you can have lesser number of servers. And the reliability is another main fact. So there are several penetration attacks that can be done in a cloud-based scenario. One of the common one is denial of service attack, or DDoS attacks. So but this is basically when someone, so a hacker or someone, jams the network by flooding it with many requests. So in case of edge computing, you don't directly need the cloud all the time, so you are less susceptible to these attacks. So that covers most topics in the application layer of system design. Thanks for watching, guys. See you on the next one.